Okay, so I'll start. Hello, everybody. My name is Quinn. I'm a PhD student from the University of Maryland. Today, I'll present the paper Debugging this OmniTable way. First, I'll talk about the motivation of the paper. So debugging is an indispensable part of programming. For simple bugs, it might be enough to just add a print statement to the code and print the values of the variables, or check if the execution reaches certain part of the code. Or a developer can use tools such as GDB to step through the program and observe how its execution state changes after every line of code. However, you're out of luck if the bug gets more complex. For example, if it involves atomicity violation, lifelock, or performance degradation. All these types of bugs are sometimes very hard to reproduce. The program might not terminate when they happen, and they don't leave behind stack trace, so you don't even know where to start. So to address this problem, the paper proposes the OmniTable query model. The idea is that you can store all architectural state of a program execution in a big relational table, and then write SQL queries on this table to answer exploratory questions that eventually lead us to the root cause of the bug. This is how the OmniTable looks like. It has a row for every executed instruction. Each row is assigned a monotonically increasing logical time, which is the first column here. That provides a total ordering of the events in the table. All the columns in the rows are the architectural execution state right before executing an instruction, like the values in all registers and the values in memory. This query model also has generators, which are tables that map low-level execution state in the OmniTable to high-level programming concepts, such as function definitions, lines of code, variable name, etc. This information is extracted from the binary of the program. Additionally, we can derive views for all the high-level concepts from this table, like the vars and the funcs view. The vars view here contain the values of all in-scope variables at each instruction in an OmniTable. So you can see here the var view has 4 columns. The first is the time of the instruction. Then the next one is the program counter, I think. And then the name of the variables and the values of the variable. And you can also have the func views, which records the time that the execution enters the function, the time it edits, the name of the function, the arguments, and the return value. So to understand how this query model is used, let's look at a case study where we want to debug a performance problem in Redis, which is a very popular in-memory key value store. So in this case study, Redis was deployed as a key value ROU cache for a slow backend. It will observe that the average end-to-end latency increased over time. And at the same time, the backend also processed an increasingly higher percentage of the requests. So the first step that the developer took was creating an OmniTable for an execution of Redis that have this issue. So from the symptom where the backend process increasingly, where the backend start to process an increasingly higher percentage of the request, we can deduce that this means there's more cache misses in Redis. So the first question to ask is, was the working set size increasing over time? So to answer this question, the developer wrote this SQL query. And what this query is doing is it looks at the funcs view and then create a sliding window of 10,000 consecutive calls to the lookup key function, and then counts the number of distinct key, which is the argument to the lookup key function, in this window. So for example, here I show a timeline when the lookup key function is called. Time go from left to right. At time 1, there's only one called with key K1, so there's one unique key. At time 2, there are two keys being called K1, K2, so the number of unique keys is 2. And at time 3, there are still only two unique key K1 and K2. So yeah, and so on. And from the result of this query, it turns out that the working set size was fairly constant. So the developer look at the next possible cause of the poor performance, which is, it could be the case that the number of items in the cache is decreasing. So the developer asked the question, was the number of items in the cache decreasing over time? Now to answer this question, we can write this SQL query, which tries the var's view and the func's view. And then it gets the values of the variable name used right before the lookup keys function is called. So this variable is used by Redis to store the number of items in the cache. So what we're doing is just simply collecting the values of the use variable every time the lookup keys function is called. And from this query, the developer found that the number of items indeed decreased throughout the execution. However, the total memory size of the cache was set to be a constant size, and the items in the cache also had the same size. So this means there's a possibility of memory leak. So the developer looked to answer the question, were there allocation size with increasingly leaking? It is leaking the bytes. So to answer the question, to write the query for this question, we need to construct a new view called define memory. There's a lot going on here, so let's just look at the following example. Here I'm showing the calls to malloc and free, and on the left is the times that these calls happen. So at time 1, the malloc is called to allocate 100 bytes, and it returned the address 01. This memory is later free at time 4. And you can see in the define memory view, the first row corresponds to this memory allocation, and it's record the time when it's allocated, the time is freed, the pointers, the address of the memory. The stack trace is essentially just the location in the code that this allocation happened, and the size of the allocation. And for allocation that doesn't have a corresponding free function calls, it will have a null values in the end column. So for example, here the second row is such an allocation, and this is a leak, and this indicate a leak memory. So once we have this view to look for the leaked memories, we just simply filter the table by the end columns, and then we can find off the leaking allocation. So with this query, the developer found that a leaking allocation site. So Redis used reference counter to manage memory allocation. So the next question is, was there a problem with reference counting? And again, to answer this question, the developer wrote a SQL query to count of the number of core to the in-graph count and degraph count, which are the function to increase and decrease the reference counts of of a memory allocation, and check to see if the number of core of the increase in ref count is equal to the number of core to the decrease in ref count. And it was found that the execution correctly called the same number of times for both of these functions. So so there might be a problem in the implementation of increase ref count or decrease ref count. And then the developer wrote the fifth query, which is the last one. This query wasn't shown in the paper, but what it does was to determine the core size of the increase ref count and decrease ref count functions, and the query found showed that the decrease ref count was called by 2 threads without a synchronization mechanism, and this called a race condition. So this is a root cause of the bug, and it was eventually fixed. So as you can see, this OmniTable query model can simplify the way that we debug the program. So here I'm showing the query on the code on the left with in an OmniTable query. It's the first query that I showed previously to determine the working set size of the execution. And on the right is a Python script to collect the same kind of data, but using GDB. And you can see that since the OmniTable query is declarative, it's very easy to read and very easy to write. But the procedural script for GDB is have to use complicated data structure like deck and dictionary, and it has to write its own code to do this to collect the same data. So up to this point, so up to this point, we have a query model, and to realize this query model to a real system, the authors built a prototype called SteamDrill. And next, I will talk now. I'll talk about the design of SteamDrill. And to materialize the entire OmniTables would be infeasible, because this table store all of the execution state, which includes the register and the memories of the execution, which can lead to very high storage and computation cost. So the solution to this is to use lazy materialization. SteamDrill uses deterministic record and replay to capture a log of non-deterministic inputs to the execution. And with this log, it can generate the OmniTable on demand by instrumenting and re-executing the original execution. This delay materialization also allows filtering unnecessary data materialization before the re-execution. And here's the architecture of SteamDrill. So in the paper, they mentioned they named this system SteamDrill, but in the figure they use the name Steamroller. But I think this is a mistake, but I think that's referred to the same thing. And the architecture of SteamDrill is similar to a typical database management system. A query will go through 3 phases: parsing, planning, and execution. In the parsing phase, it uses conventional SQL parser to get a tree of relational operations. In the planning phase, there are 2 parts: logical planning and physical planning. In logical planning, it optimizes the relational tree with standard optimizations. And in physical planning, it produces a staged execution plan, which eventually feed to the execution phase for to be executed. So here's an example of parsing a SQL query in SteamDrill. So this query is used for identifying use after free instructions. And it's a choice between an inst views and the defined memory view, and you can see it on the right. The defined memories is itself is a view, so it also has its own tree, and you can see that this initial relational tree is very inefficient because it has to materialize all of the data before it, and then it filter the data in the end. So it's very inefficient. Now in the logical planning phase, SteamDrill optimizes the tree using standard optimization like predicate pushdown. And most importantly, it determines an efficient choice order. So on the right, in the figure on the right here, you can see of the filters, it's the sigma nodes are pushed down close to the FD node. The FD nodes are the generators table. I think it stands for function definition. And the OT node stands for OmniTable, which is the node for materializing the OmniTable. Also note here is that the OmniTable is put on the right branch of the join node, and the FD table is put on the left branch. This is because by doing this, we can skip some materialization of the OT node using the values fetched from the FD node, and this is a better choice order. Now in the physical planning phase, SteamDrill assign the operation or the operators into stages. Each stage corresponds to a new replay execution, so it will try to use as few stages as possible. So for example, here the stages are in parentheses, and you can see there are 3 stages for this query plan. And after this, this final query plan will be used for execution. Next, let's look at the evaluation of the query model and SteamDrill. The first experiment that the authors performed was to measure the programming complexity of OmniTable query model versus GDB. They performed 5 case studies on popular open source applications like Memcache, Redis, and SQLite. They implemented 14 debugging queries using OmniTable queries and equivalent Python script for GDB. Now, on average, they use 3 metrics. The first metric is lines of code, the number of lines of code in the script. The second metric in nodes, which is the number of nodes in the abstract syntax tree. And the final metric is the house stack complexity, which estimates the amount of time it would take to correctly produce the query or the script. And on average, OmniTable requires 3.7 times fewer lines of code, 1.7 times fewer number of nodes, and 2.7 times less estimated time to develop. The next experiment compared the query latency between SteamDrill and GDB. They chose 3 representative queries from the case studies and compare SteamDrill that's run on a single core with SteamDrill that's run on 64 core and GDB. And they found that SteamDrill is 2 to 290 times faster than GDB on a single core. And the 64 core SteamDrill is 6.92 to more than 1,800 times faster than GDB. So in conclusion, they introduced a new query model called OmniTable that reduced programming complexity and performance overhead of debugging. They realized the model in a system called SteamDrill, which uses lazy materialization and declarative query optimization to overcome the extreme size of OmniTable. And the evaluation showed that the system accelerates debugging queries by an order of magnitude compared to state-of-the-art tools. That's all I have for today. Thank you for listening.
All right, thanks a lot for the detailed presentation. Yeah, let me stop the recording.